In the first video in this module, we talked about some fundamental properties of waveforms, particularly amplitude and frequency and phase. I posed a question at the end of that video about whether that was enough to describe how we actually hear sound in the real world. And so in this video, we're going to talk about a very brief introduction to the field of psychoacoustics, which is about that question exactly, how we hear sound and how that might differ sometimes from how we represent it in the real world or how we measure it. So we're going to talk about loudness as a notion that's a little bit different from the amplitude that we were talking about in the first video. We'll talk about pitch as something, again, that's a little bit different from frequency as we talked about it in the first video. And we'll talk about a few other ways that these intermingle towards the end of the video. So I want to start off with a quick question for you. We have here, as you can see, this is actually a sine wave. It's kind of compressed on the time domain. This is a 10-second long sine wave that's starting at 0 amplitude, and it is getting bigger and bigger over time. Its amplitude envelope is increasing, as you can see, until it's at full amplitude, in the full -1 to 1 range at the end. So what I want you to do is listen to this. You can see this is a linear ramp. It's increasing linearly from 0 at the beginning to 1 at the end. So I want you to listen to this and listen to whether you hear it is increasing linearly or not. Okay, so I don't know about you, but I don't hear that as increasing linearly. I hear it much more as increasing kind of like on a curve like that. So it seems like it's getting louder really fast at the beginning and then slows down and slows down and slows down and slows down. And the reason for this is that we don't hear the linear increase in amplitude linearly. So amplitude goes from -1 to +1, but what we hear is something more that we describe as loudness, which has a logarithmic relationship to amplitude. So for every 10, we measure loudness in a unit called decibels, which we abbreviate as dB, but to write that out, it's actually decibels. And for every 10 decibels that we increase, we get twice as loud. And so this reflects what you just heard in the example, that we're not perceiving this amplitude as increasing linearly, but rather our perception of it is on this logarithmic scale. Something I want to emphasize about both amplitude and loudness, this is a really important point about how we're using these terms in this course and how they get used a lot in music technology, is that they're relative measures. They're not absolute measures of how loud something is in the real world. And there's a very important reason for this. If you think about amplitude, it's -1 to +1, what? And the answer is really nothing when we're looking at that waveform on the computer, because when the computer's playing back a sound, we have no idea how how different things in the chain after that computer are going to affect the sound. How loud is the amplifier it's hooked up to? How loud are the speakers? How far away are we standing from the speakers? So how much are the sound waves kind of losing their energy as they go from the speakers to us? We don't know any of that, so we can't affix kind of absolute units to amplitude as we look at them on the computer. Instead, it's a relative measure, so we know that +1 is more than plus 0.5 is more than 0.25, and so on and so forth. And the same thing is true of loudness. If you look at a mixer, for instance, this example on the right here, that is a physical mixer, like someone might use at a concert or in a recording studio. And this example here is from the Reaper digital audio workstation program, a virtual mixer that's controlling the loudness on a channel. And you can see the units here in this virtual example. We have 0 here. Let me switch to different colors so you can actually see this. We have 0 there. That's 0 decibels. That just means whatever sound is coming in is not making it louder, it's not making it softer. Above that, we have +6 and we have +12. And then down here, we have -6, -12, -18, -24, and so on and so forth. And so, again, this isn't speaking to a particular measure that we can measure in the real world of this sound. It's just saying, well, the sound is coming in at a certain level, and then I'm either leaving it alone, 0 dB, or I'm increasing it by a certain amount, or I'm decreasing it by a certain amount. So when we look at mixers, either virtually or in the real world, that's how we tend to think about loudness. And And we're using decibels here as a measure of loudness rather than amplitude, because then moving these sliders has more perceptual psychoacoustic relevance to us because of that logarithmic scale. Let's move on now and talk about pitch for a second. You may remember from the first video I played this chirp sound. It went linearly from 20 hertz all the way up to 20,000 hertz with a sine wave. So over 10 seconds it went from 20 hertz all the way up to 20,000 hertz. I want you to listen to this again with a similar question that I asked about that amplitude envelope at the beginning of this video. Do you hear it as increasing linearly in pitch, or do you hear it as increasing at some other kind of scale? So go ahead and listen to this. As you were hearing this, the basic idea here is that it was not increasing linearly. It seemed like the pitch rose very quickly at the beginning, and then it got slower and slower and slower and slower as it went on. In other words, that same kind of logarithmic curve that's leveling out as it gets higher and higher. And that's because, unsurprisingly, there's different ways that we can think about pitch and pitch relationships. As we're thinking about frequency, we can think about frequency as going up linearly. And there's a key musical construct that describes this called the harmonic series. So if we have a base frequency at, say, 100 hertz, we can think of integer multiples of that. So 2 times 100 is 200, 3 times would be 300, 4 times 400, and so on, 500, 600, and on and on and on. This harmonic series is very important in music. And we can think about these hertz as representing, if our base frequency were to be, to represent this low C, then when we double that frequency, we would be the C an octave above. When we go 3 times that original frequency, we would be the G above that. And when we went 4 times, we would be the C above that. And so we're not always getting C's. We're getting different notes. If we went up from there, we would then get an E, and then we get a G, and then a kind of B flat, and so on and so forth. But there's another way to think about pitch, which is in terms of octaves. And this is not a linear scale of 1 times, 2 times, 3 times, 4 times anymore. This is a scale of doubling every time. So 100, 200 hertz, 400 hertz, 800 hertz, 1600 hertz, and so on and so forth. And if we go at those frequency ratios, always doubling, rather than always multiplying by some integer multiple, we end up with successive octaves where they're all C's, from C to C to C to C. And so you see, get C, we double it, we get the C the next octave up. We double that, we get the C the next octave up. We double that, we get the C the next octave up. And so again, the way that we hear pitch is not on this linear frequency scale, but on this logarithmic octave scale, because we hear these C's as sharing something in common with each other. And going from one C to the next is traversing this space of an octave, even though the difference between 100 and 200 hertz and between 200 and 400 hertz is different in hertz space. It's 100 versus 200. Again, there's this difference between how we represent things in frequency and how we hear them in terms of these octaves, this pitch, this logarithmic relationship. I want to go a little bit further than that because we hear something else that's a little bit more complicated too when we're listening to pitch instead of frequency. So here are two frequencies, 2 sine waves. One is at 440 hertz, the one on top. And then the one on the bottom is at 880 hertz. So this is a 2-to-1 relationship. So they're an octave apart from each other. Now what happens if we actually listen to these? I'm going to switch over to Reaper here for a second so that we can hear this. When I play these together, here's my 440 hertz sine wave, and here's my 880 hertz sine wave. I'm going to go ahead and play this. And think about how many different pitches you think you're hearing. Okay, that's enough to get an idea there. So when I hear this, unless I'm really, really concentrating, I'm really just hearing what I feel like is one note or one pitch. But if I go ahead and play this again and just play the 440 hertz one, you hear that very clearly. Or I play just the 880 hertz one, you hear that very clearly. But when I play them together, we hear something very different. Just like some melding of these, because they have this special relationship to each other. And this is something that's more, even more evident if we go to real-world sounds. So if I come over here, this is actually trombone sound, a low E on a trombone that you can hear. But we're not actually hearing the original trombone sound here. We're hearing a bunch of sine waves. I can show you what I mean here. I'm going to play just that lowest sine wave. And then I'm going to play the next one up with it. And the next one up. And the next one up. You're hearing these individual things. This is actually a harmonic series, so it's going up 1 times, 2 times, 3 times the bass frequency. And as I click a few more in here, you'll eventually stop really noticing all the individual ones, and you'll start hearing it as a trombone. It's really starting to sound like a trombone now, the more of these I add in. So we're not hearing these as individual sine waves, as individual frequencies anymore. We're hearing them as a composite pitch. And that pitch we're hearing in this case is this low E. We'll return to that demo again in a later video and delve into some of the details of that a bit more. The point here is that it's not just the difference between a linear and a logarithmic relationship in terms of frequency and pitch, but it's also a difference between making out individual frequencies and hearing them melding into some bigger composite results. I want to cover one more thing before we leave our discussion of psychoacoustics for now. I want to play this chirp one last time for you. And this time I want you to focus on how loud it sounds over the course of the chirp from 20 hertz to 20,000 hertz. Does it sound like it's ever getting louder and softer, or does it sound like the loudness is the same the whole time? Okay. So the loudness is obviously changing as that goes from 20 hertz up to 20,000 hertz. The amplitude of that sine wave in the file is actually not changing at all. It's using the full -1 to +1 range throughout. But our perception of that is changing based on the frequency of the sine wave. This is explained by this phenomenon called the Fletcher-Munson loudness curves. What this shows is that on our y-axis here we have decibels, and on our x-axis we have frequency. If we follow one of these contours here, if we're changing our loudness here as we go up, we actually perceive that curve as being the exact same loudness throughout. So in order to get something that sounds like it's equally loud from 20 hertz all the way up to 20,000 hertz, we actually have to change its amplitude in order to kind of fake our ears into hearing it sound like it's the same. Because our ears are more sensitive to a broader range of dynamics, especially in this particular range here, around 3,000 to 5,000 hertz, than they are, say, at the very low end of the spectrum or even at the very high end. So this is another example about how frequency and loudness come together in our brains as we're hearing sounds to create effects that are very different from what we might see if we're just looking at a waveform. So to review what we've covered in this video, we've talked about psychoacoustics as describing how we perceive sound and not just how it exists acoustically in the world or how we might represent it as a waveform. We particularly talked about loudness versus amplitude, and we talked about pitch versus frequency. And we looked at the Fletcher-Munson loudness curves as a really good example of this. What we're going to talk about in the next video is if we have two sounds that actually have the exact same pitch and the exact same loudness, but they sound really different from each other, well, how do we describe that? So we'll be talking about timbre in the next video.